So in this session, we are going to understand how a deep neural network is trained. We are going to talk about a simple case. First we'll talk about a simple case where there's only one output node, which is either, let's say we are predicting 1 or 0. As I told you in the previous sessions, that in order for us to be able to train the model, we need to be able to find the values for the parameters theta, which is present for each of these hidden nodes. And we have thetas like that all over for each hidden node, right? So essentially I want to compute these thetas such that some sort of a loss function is minimized, and we talked about the fact that we often use a loss function which is nothing but the maximum likelihood of the model, right? So I try and maximize the summation of log of each sample that I have. Let's say I have m samples, and I try and maximize this sum, right? And this is the probability by which, so this function, probability function, is nothing but the composite function that this node is seeing, right? Like if I make a whole composite function, I define in terms of my inputs a function that this guy is seeing, and I want to maximize this, right? So I said that to do that, we use gradient descent, which basically means that each parameter theta, I'm going to update it by using the derivative of the loss function. So this is the revision part. This is what I'm trying to achieve, and this gives us a problem that we need to find the derivative of the loss function with respect to the theta, right? So for each of the theta, literally all the parameters that we have, we need to be able to compute the derivative of the loss function with respect to that theta, right? And then finally, once we've updated all theta, we will know the new loss that we have, and then maybe we can keep doing this until the loss is sufficiently low. Now, let's take a look at how we are going to compute it. And how we are going to compute it is using a technique known as back propagation. So back propagation is a technique to compute derivatives efficiently, in the sense that if I have to compute a derivative, let's say this is some function, right? I can always express this function in terms of combination of this function, in terms of combination of this function. So this function would come out to be some huge function, and I can take the derivative with respect to it, right? And then I'll have to do that for the other parameter as well, and then for every parameter out there. And there are literally millions and hundreds of thousands of parameters here, right? So the key thing to note that if I do that, there will be a lot of recomputation. To give you an insight into why there is any amount of recomputation involved in computing the derivative of a function that would look like the one that is provided to us by our deep network, and to understand what is the basics of the back propagation algorithm that we're going to be describing soon, I'll have to explain you two simple calculus concepts for derivatives. The first one is how do we compute the derivative of composite functions, right? So let's say I have a function f which gives me an output y, and it is a function of x, right? And I have a function g which is a function of y, and it gives me the output z, right? Now let's say I have to compute the derivative of z with respect to x. How do I do that, right? Now one way to do that would be if I replace everywhere where I have y, right? If I replace it with f of x, and let's say g of y was e to the power minus y square, right? So this would turn out to be e to the power minus f of x ka whole square, right? So now I have z directly in terms of x, right? And maybe f of x I can expand f of x as well, and then this would be completely in terms of x, right? But let's say, and then I can just differentiate it with respect to x, like using my differentiation tools, I can do that, right? But let's say I really do not know, I have no way of directly substituting it, right? Also, I don't want to substitute it, right? In that case, the derivative rules say that the derivative of z with respect to x is the same as derivative of z with respect to y multiplied by the derivative of y with respect to x. And I don't know if there's an intuitive way in which I can explain you why that holds true, but if you apply the definition of derivative and if you substitute these two differentials, multiply them, and you effectively get that. This is one of the fundamental guiding theorems that I'm going to use to calculate the gradients that I need to in an effective manner. Let's say I had a whole chain of these events, right? So let's say there's a chain of these things, right? So if I have to calculate the differential with respect to the first member, I can do that by, so this guy is really far away from this guy, right? The output, the actual output, right? So let's say I have to find out, let's say I call this node x1 and this is my output node and the value is z. So if I have to find out the z with respect to the x1, I can find it out by continuously replacing the guy which is dependent on this by saying that, let's say this guy is x2 dx2 dz upon dx2 upon dx1. Okay. So if I know how to differentiate, how to have the differential among these two elements, right? I've shifted my differential to one stage back, and then I can do the same thing with x2 in the chain and keep finding these differentials and multiplying. So what you directly notice here is that I have to find out these differentials dz upon dx2 for the computation of this, right? But I also might need to compute dz upon dx2 for the computation of this, because this might also be dependent on this. This also might be a line that's going through, right? So I need to calculate this value twice. If I did not use my algorithm, I'd be computing dz upon d2, dx2, let's say this is x3, right? And let's say x3 is going through x2 and so on, right? And I'm right now I'm describing a scenario where there's only a linear chain. I'm not assuming that the chain is non-linear. We're gonna have to talk about that case. That's the next thing I'm gonna talk about. Assuming the chain is linear to the output variable, I can keep using my formula for calculating the differential for composite functions in that manner, right? But I end up having terms which are getting recomputed. So I don't want that. And what if I did this computation, I cached these values, right? So this is what is the general principle of dynamic programming, is that if there are sub-problems which need to be computed again and again, then I store the values of those sub-problems and I reuse them later, right? Or what is known as memoization. And then dynamic programming goes further ahead and says that if what you can do is that instead of memoizing, you can solve the same problem in a bottom-up manner, in the sense that whatever term that you need for a particular problem to be solved, solve that term before solving this term, right? So you always have all the terms, all the values that you need. So in this case, what it would look like is that I'm going to calculate the differential of dz with respect to dz first, which is 1, right? And then I'm going to calculate a differential of dz with, let's say, this value was x100, right? So I'm going to calculate the differential of d x100, and that's probably just simple because I just have one relationship, and I can just directly substitute whatever the formula is and calculate this differential, right? So that's easy. And then I compute this for all of these. Now, all the nodes that are in the layer right before this, their differentials according to my formula would only really depend on the differentials of this layer, right? Because they're connected to this layer. This is the parent layer. And I know the differentials for this layer. So now I know the differentials of this layer, provided I know the differential also of this guy with respect to this guy, which I can calculate. And then the same argument keeps on applying. So I can calculate the differential of each of these nodes with respect to my final output z in what is known as a bottom-up manner. So this is why this algorithm is known as back propagation, because we are propagating the values of gradients backwards. Because of the chain rule of calculus that we have, we are propagating the gradients backwards. So that's the first thing, the backward propagation. The second thing is, I told you, right, that there is a loss function here. For me to be able to calculate the value for the loss, I must actually have the value for the function itself, right? And that value depends on what value have I chosen for thetas currently, right? My parameters, what values I have chosen for parameters currently. And before the back propagation happens, for me to be able to define my loss function, I need to first do a forward step and calculate the values that are present at each of these nodes, right? So the value that will be present at each node is whatever my inputs are, right? And then maybe this step is just the inputs multiplied by the weight and summing them up, and then passing through the whatever rectified function that we have, and similarly, and so on and so on and so on, right? And we'll finally have a value for 6. So that is what is known as a forward propagation. We need to actually have the values of all at each step all the time in order to be able to drive this algorithm, right? So there's a forward propagation, and then there's a backward propagation, which is nothing but our way of calculating the gradients, how we are calculating the gradients. In fact, back propagation is a general name for a technique to calculate gradients, and that's all it is. We use the assumption that we have a linear chain. I'm not considering the case that x1 is actually being used by many nodes in the next layer. Right? And to be able to understand that, we'll have to talk about another principle in calculus, which is known as total derivative. And total derivative says that if you, let's say there's a function f, right, and it is dependent on 3 parameters x, y, and t. If I have to calculate the derivative of f with respect to t, what?
Assume x and y is constant.
X and y are not constant with respect to t. So as I modify the value of t, the value of x might get modified. So what I'm essentially trying to say is that x is another function g1 of t, and y is another function g2 of t. So as t gets modified, x and y also get modified. In that case, I cannot just calculate the derivative of f with respect to just t, assuming that x and y are constant. And in this case, how we calculate the derivative is by using this formula. And I don't know how this formula is derived, but let's talk about this nonetheless. Maybe it's not very complicated to derive it, but we can definitely talk about what does it mean. Essentially, what this formula says is that if you have to calculate the derivative of f with respect to t, you calculate the partial derivative of f with respect to t, and the derivative of t with respect to t, which is just 1, and then you add that partial derivative of f with respect to x and the derivative of x with respect to t, and so on for y. And then you can multiply the whole thing with dt, and this is what you get. So what does this mean? That the partial difference in the value of f is coming from three sources. It's coming from some value multiplied by the difference in t, plus some value multiplied by the difference in x, plus some value multiplied by the difference in y. That value is nothing but the partial derivatives, right? So this kind of makes sense, right? That the difference in a value of a function would come from if I make some modification in one of the axes that it has, and then see, hey, what's the gradient that I get there? Let's multiply the gradient that I get there with respect to how much amount I moved, and then add the same value for all the other dimensions that I have, right? So this kind of makes sense. Essentially what this has told us is that if there are other dependent variables, in the chain calculus rule that I have, it says that at any point if there are more than one dependent variables, I just sum the differentials for all of them. So what that would mean for our case is that if I have to calculate the differential with respect to x1, if I have to calculate the difference of, let's say, a final output z with respect to x1, and let's say this is x2, this is x5, this is x6, right? And x1 is being used by x2 and x5 and x6, right? So essentially the derivative of z with respect to x1 is going to be the sum of all the branching that we have, right? And this essentially completes our backpropagation in the sense that we calculate the derivatives here of z with respect to all these variables, and then when we want to calculate for any of the previous layer, we sum for all the values that it's using, and so on, and we keep propagating it until the very first layer, right? So this kind of concludes what backpropagation is about. This is essentially what backpropagation is about.